In this chapter, we work on the inventory routing problem, also called the integrated inventory and routing problem. The goal is to make two decisions together: when and how much to deliver, and in what sequence vehicles should visit customers. This integration matters because transportation cost and inventory holding cost trade off against each other. If you deliver too often, routing cost explodes. If you deliver too rarely, you create stockout risk or require excessive safety stock. Imagine a regional distributor of medical supplies serving dozens of clinics and small hospitals. The distributor operates a central warehouse and is responsible for replenishing customer inventory. Clinics have limited storage capacity and semi-predictable consumption. A stockout is a major service failure, while overstocking wastes space and ties up working capital. So, the distributor needs a proactive multi-day plan that balances both service level and cost. This is an integrated problem because routing alone does not say when to visit, and inventory control alone does not say how to move vehicles efficiently. If you solve them separately, the operation becomes reactive, with expensive emergency trips and unstable inventory patterns. A coordinated plan schedules visits and quantities to keep inventories within desired ranges while bundling stops into efficient routes. Tier 1 frames the distributor as an agent making decisions over time under uncertain demand. Each day you observe inventories, choose routes and delivery quantities, and then demand is realized. This framing is useful because it forces you to define the system state, the set of feasible actions, how inventory evolves, and how cost accumulates over the planning horizon. This slide lists the sets and indices. We track a set of time periods, a set of nodes that includes the depot and the customers, and a set of vehicles. These sets define the scope of the planning problem and make it clear that the model is multi-period and network-based, not a single-day routing snapshot. The state at a given time is the inventory level at every location, including the depot and each customer. Operationally, this means the planner has a full snapshot of how close each clinic is to a stockout and how much space remains. This is critical because routing decisions should prioritize customers that are at risk, not only customers that are geographically close. An action combines two things: a set of vehicle routes and a set of delivery quantities. So you decide who gets visited, in what order, and how much inventory is delivered. Feasibility is where operations come in. Vehicles have capacity limits, routes have time and distance implications, and customers may have receiving constraints. This slide shows the inventory transition. After deliveries, random customer demand consumes inventory, and that creates the next state. This update rule prevents hand-waving. It is the explicit link between today's routing decision and tomorrow's inventory risk. The reward is defined as the negative of total cost for the day. That cost has two main parts: transportation cost for the routes and inventory holding cost for inventory stored at the depot and at customers. This structure forces the policy to balance frequent deliveries against higher holding levels, while still keeping service levels high. Here we define the overall optimization goal. Find a policy that maximizes expected discounted reward over the horizon. In practical terms, you want to minimize total expected cost across the planning horizon. Discounting is a standard mechanism that emphasizes earlier costs and outcomes, and it helps the planning process remain stable over time. The Bellman optimality equation is the core recursion behind dynamic programming methods. It says that the optimal value at a state equals the best immediate reward plus the discounted expected value of the next state. For small problem instances, you can compute this with value iteration or policy iteration. The limitation is that the number of possible inventory states grows extremely fast as you add customers. This diagram illustrates how the system evolves from one day to the next. Inventories define the state, the distributor chooses routes and quantities, and then demand drives the transition into the next day. Use this picture as a mental model. Every improvement method in later tiers is still trying to manage the same cycle, just with scalable approximations. When the instance is small, classical dynamic programming can work. But as the number of clinics grows, both the state space and the action space explode. This is why real-world inventory routing problems typically rely on heuristics and meta-heuristics that can produce strong solutions quickly, even if they are not provably optimal. Tier 2 introduces a classic meta-heuristic called greedy randomized adaptive search procedure. It repeatedly constructs a feasible solution and then improves it with local search. The combination of greediness and randomness is important. Greediness gives you good building blocks, while randomness helps you explore many different solutions instead of repeating the same pattern. In the construction phase, you build routes step by step. Instead of always selecting the single best next customer, you create a restricted candidate list of several good options. Then you randomly select from that list. This small injection of randomness helps the algorithm escape predictable behavior and increases the chance of finding a better overall routing and replenishment pattern. After a complete set of routes is built, local search improves it using neighborhood moves. For routing, typical moves include swapping edges to remove crossings, relocating a customer within a route, or swapping customers between routes. Local search continues until you cannot find a better neighboring solution. The result is a higher quality plan than the initial construction alone. In this part, the code makes the slide method executable. Key functions in this chunk include get cheapest insertion cost and construct solution. You will notice logic related to demand, inventory, route. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, you can see the implementation details in action. Key functions in this chunk include local search to opt and grasp for IRP. You will notice logic related to demand, route, iteration. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, the code makes the slide method executable. You will notice logic related to inventory, route, iteration. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. Tier 3 uses the whale optimization algorithm, a nature-inspired meta-heuristic based on humpback whale hunting behavior. A complete multi-day replenishment and routing schedule is treated as a candidate position in the search space. The fitness function is the total system cost, combining transportation and inventory holding. The algorithm updates a population of candidates over many iterations to search for lower-cost schedules. Whale optimization balances exploitation and exploration. Encircling prey and bubble net attacking intensify the search around the best-known solution, while search for prey pushes the population into new regions. You need both behaviors. Without exploitation, you do not refine good solutions. Without exploration, you risk getting stuck in a local optimum that looks good but is not truly best. This figure summarizes the whale optimization search strategy. The spiral motion represents a fine-grained approach toward a promising solution, while the random movement represents global exploration. In inventory routing terms, this translates into both refining a strong schedule and also discovering alternative delivery patterns that might reduce cost or improve service stability. Tier 4 addresses demand uncertainty using a generative adversarial network. Instead of assuming a simple distribution, the goal is to learn realistic demand patterns from historical data. Once trained, the generator can produce many plausible future scenarios. You then evaluate routing and replenishment policies against this scenario set to choose a plan that remains strong under uncertainty. A generative adversarial network has two parts. The generator produces synthetic demand scenarios, and the discriminator tries to distinguish synthetic scenarios from real ones. Training is adversarial. The discriminator becomes a better judge, and the generator becomes a better forger. The outcome you want is synthetic demand that is statistically similar to what the clinics actually experience. This diagram shows a typical generator and discriminator architecture for demand scenario generation. The key idea is that the output is not a single number, but a multi-customer, multi-period demand time series. In practice, this lets you stress test your inventory routing plans across many correlated demand realizations, which is much closer to reality than independent point forecasts. In a robust planning workflow, you generate a large scenario set and solve the inventory routing problem repeatedly. Then you select a policy that performs well across scenarios. Depending on risk appetite, you might optimize for average performance, or you might optimize for worst-case outcomes to protect service levels for critical clinics. Tier 5 introduces an integrated digital twin, which is a real-time simulation of the distribution system. It tracks inventory at the depot and customers, vehicle locations, and operational constraints. Because it ingests live signals like traffic, weather, and point-of-sale demand, it can continuously replan and test how decisions will play out before execution. This architecture diagram shows how real-world data streams feed a digital twin. The twin maintains a live state and lets the optimizer evaluate alternative delivery plans. The practical benefit is resilience. When conditions change, you can quantify the impact and re-optimize quickly instead of relying on ad hoc decisions. What-if analysis is one of the most valuable digital twin capabilities. You can test disruptions like snowstorms, traffic incidents, and vehicle breakdowns. The twin provides quantified outcomes such as expected additional cost or increased stockout risk, which supports proactive mitigation like shifting deliveries or adding temporary capacity. Tier 6 moves from a centralized planner to distributed intelligence. Customer agents raise replenishment tasks when inventories are projected to fall below thresholds. Vehicle agents bid on tasks based on distance, remaining capacity, and current route structure. The system self-organizes, and efficient routes emerge from local decisions and coordination. In the Centaur model, the goal is not to replace the human planner, but to combine strengths. The system proposes several high-quality plans, and explainable interfaces provide the reasoning. The human then adjusts the plan based on real-world context, such as receiving policies or temporary road closures. Those edits feed back into the system so future proposals better match operational reality. As systems become more autonomous, you need value alignment. An ethical governor constrains the optimizer so it cannot sacrifice fairness, sustainability, or labor compliance for marginal cost savings. For example, fairness constraints prevent systematically neglecting remote clinics. Sustainability constraints enforce fleet carbon budgets, and labor rules protect driver safety and compliance. This diagram illustrates ethical governance as a supervisory layer. The optimizer proposes a plan, and the governor checks it against higher-level constraints before execution. In practice, this helps ensure that cost-minimizing behavior does not create unacceptable service inequities or regulatory violations. Tier 9 highlights a quantum classical approach called the Variational Quantum Eigensolver. Inventory routing is computationally hard, so new methods attempt to scale beyond classical exact solvers. VQE maps the objective into a binary optimization form that then uses a parameterized quantum circuit and a classical optimizer in a feedback loop to search for low-cost solutions. This cycle diagram shows how VQE alternates between quantum evaluation and classical parameter updates. The quantum processor estimates the objective value for a candidate circuit state. The classical optimizer adjusts parameters to reduce that value, and the loop continues until convergence. The hybrid structure leverages strengths of both compute paradigms. It is important to separate roles. The quantum processor performs state preparation and measurement, which explores a large configuration space. The classical processor handles the optimization logic that tunes parameters. Without the classical loop, the quantum processor does not know how to steer toward better solutions. Without the quantum evaluation, the classical optimizer lacks access to the quantum state landscape. Tier 10 focuses on demand shaping. The idea is to influence delivery timing by offering incentives so that more orders shift into route-efficient windows. By identifying expensive delivery days and cheaper bundling opportunities, the system can fund discounts through operational savings and create a more stable and efficient delivery pattern. These practice questions test whether you can translate the ideas into concrete reasoning. For Tier 1, you describe a state, an action, and an inventory transition. For Tier 2, you compute a restricted candidate list and explain what the parameter controls. For Tier 3, you articulate why exploration and exploitation must coexist in meta-heuristic search. These questions focus on uncertainty and simulation. For the generative adversarial network, you diagnose why generated scenarios might not match reality. For the digital twin, you identify data streams needed to model spoilage risk and propose a what-if scenario. For distributed intelligence, you explain how vehicle bidding can lead to route formation. These questions connect human oversight, ethics, quantum approaches, and market shaping. For the Centaur interaction, you describe how explainability supports human correction. For ethics, you propose a specific constraint to guarantee fair service. For VQE, you clarify the hybrid roles. And for demand shaping, you propose an incentive policy and recognize a potential unintended consequence. The key takeaway is that inventory routing is not just a routing problem, and not just an inventory problem. It is a dynamic decision system where daily routing choices drive future inventory risk. A practical toolkit moves from rigorous sequential modeling to scalable heuristics, robust planning under uncertainty, real-time digital twins, distributed autonomy, human oversight, value alignment, and even strategic demand shaping.